Okay, so let me find one last mention of this topic is so this change of variables. Okay, so make something up. So you have this model which is number one, and um, it comes from a model from a description of the population dynamics with natural growth or decay plus, well, natural or not, but the influx or outflux of people as an additional feature. Okay, so and then we did a substitution, which is right there in the box, or rather the actual we introduce a new variable. Okay, which is y minus a. So y is the original population, z is the new population, which then what is it? It is totally made up. Okay, so but then the differential equation is simpler. We solved it in such a way that actually a particular choice of A would eliminate what? It eliminates the extra term. It does not disappear automatically. So that term that makes B, the term B, what makes it impossible. Okay, so this is it's not only new, but also it is a problem. So because we don't know, well, technically we don't know what to do with it, or we actually do, but suppose we don't. So then so that extra term called well, my plus b, you can tell it is actually, what is it? It's a like a linear function, but then is there that y-intercept term or not? So it's not just because you don't want it to have it. You cannot just eliminate it, by will. So we did the substitution, which produced a new variable z, and that variable z would have no extra term if a is chosen this particular way, and that value was quite. Where's that value? Right here. So it was not to be predicted early on, even though we knew there's something like that coming up. But we did not know what that value was. So remember, it appears to be a shift. Okay, and so we knew that there was a shift. We didn't know what that shift was. We discovered that with that shift is that kind of eliminates this feature of influx outflux, and it is entirely exponential growth decay dynamics of population. Okay, so that's and you saw that they go back. You can forget about z altogether. Okay, so there's nothing wrong with that. So it's entirely it's entirely about y. Y is the solution, and here we're done here. Okay, so then the point was that I was trying to think of it. Let's make it an exercise. Is it what is there a meaning? A meaning for z. Okay, so which once again, it isn't. It's great. We don't really need it for a solution. But if our model is that, so y is the exponential model with a shift. So what is the meaning of the shift? So best I can tell, I thought about it. The only thing I can think of, which is creates that model. Well, it is the answer is zombies. Okay. Okay, so part of the city is made of zombies, and they neither die nor they reproduce, and so it stays forever there. And the rest of these are people, and the population grows. So there's a wall. Okay, there's a wall that separates the city, and then but for some reason we decided to look at the population as a whole, including the zombies. And so in that case, we have this kind of model that. People are producing in a normal way, but the zombies do not, or nor do they die. Anyway, all right. That's the thing. Okay, so the topic is back to the discrete. Remember the limit. So back to from what? From the limit. From after the limit delta t goes to 0. Okay, so what if we have to go back? So why do we have to go back in the first place? And the answer is even though the model that the situation that we have accepted by now, I hope, is that you start with a model and verbal description, and then you produce possibly a difference equation, and then from it with a limit, right? You produce an ODE. Well, that's what we have had so far, but it's quite possible that you're not in the position, you're not responsible for this. So this is out. Okay, so somebody gives you the ODE. Somebody did the job and they produce a model, And it doesn't matter what that model is, you have an ODE, period. Okay, so you don't have to reproduce the model or anything or do anything like that. So what do we do with that? In that case, we already have some ideas, and we have algebraic solutions, separation or substitution. Once again, it has nothing to do with where the model came from. It's entirely abstract at this point. We know about the theoretical analysis existence and uniqueness, once again, to confirm that your model is good. And thirdly, numerical analysis. What is it, the numerical analysis? It's that's a back route. Okay, that's what it is. Back to the discrete difference equation. So we take the limit, we had a difference equation, we took the limit, ended up with a differential equation. So with differentiability and everything, more recent topic. So why would we solve? So if this fails, okay, so then if it succeeds, then we're done. If it fails, then we turn towards the bottom row, and then a numerical analysis is inevitable. Fails meaning that we cannot find a good substitution or separation variables to find a solution as a single formula. In which case, yeah, we still want to do something and say something useful about the ODE. And the answer is numerical analysis, which is identical to the difference equation. So we have to just undo the limit, which is really not much of a job. It is what does that mean? So backwards. So the limit turns. Remember, when you go with the limit, what happens is dy become rather the other way around. Delta y becomes dy. Delta t becomes dt. And here we go in the opposite direction. So it's quite literally. Quite literally, your differential equation is dy dx dy dt is equal to, say, f of y, and now we're going backwards. Okay, so we replace the d's with deltas, and that gives me once again a numerical recursive equation that can be an approximation of our solution. Okay, so once again, let's do that again. So this is our function. The fact that is it autonomous or not makes no difference. That presence of t over there is what makes it autonomous or not. For numerical analysis, we're not concerned with complexity. What might cause it to fail our algebraic solution is complexity. With the numerical approximation, we don't care. It's just fine. It makes no difference because we're plugging in numbers into it. Doesn't matter how complex the function is. It's computable. That algebraic calculus, calculus 1 and 2 methods that apply, and they're done by hand, and so complexity stands in the way. And so, okay, so suppose we don't care about that anymore. So this is what the picture is familiar already. So in this case, this is an autonomous differential equation. So for various initial conditions, we're just supposed to proceed one step at a time rather than producing the whole curve at once. Okay, so and we follow the slopes. Okay, so the slopes are plotted as many as necessary in order for us to jump from. These are the jumps, by the way. This is the only thing that is why it becomes a jump, because after all, we know all the values of f are known. This one is defined on a rectangle, say. So all of these rectangle right here. So why do we jump? Because we make t jump. Okay, so we make the time incremental, which makes kind of we are moving through space also in incremental fashion. But otherwise this everything kind of continues. So it's just the way we choose to do it. So the slopes are pre-plotted, and then you just jump from one to the next as we did before, except this time it is where does it come from? So if I were to rewrite this, I have dy dt equal to f of ty. And then backwards from the limit, I have right delta y over delta t is equal to f of ty. And then I produce my recursive equation like this. This is my recursive equation. So the increment of the vertical is computable. So if we know where we are and what time it is, we just compute the right hand side, and then we know how far we're supposed to step. How far we're supposed to step along the y-axis. Okay, so that what we need to work out. So that would be incidentally. So that would be it. And we'll do a little bit more than that, a little bit more in the sense that I don't want to entirely break the connection between the two. Okay, so I want to actually see more clearly what's the relation between the ODE on one hand here and the incremental solution that we have here. Okay, and the answer is here we are moving on a tangent. Okay, so moving on a tangent away from the curve that we don't know. Well, why don't we're looking for that curve, the solution of my differential equation. We do not, because we are unable to. So suppose but that curve is somewhere. For example, if it is, we have a existence, for example, that can be established a priori. And so suppose we know that there's a curve there, and then but we don't know where it is, what it looks like. So what does our solution look like relative to that curve? And that's what is in the middle. Okay, so the unknown curve is approximated by its known derivative. Derivative is right here, right? Derivative. We know what derivative is. At that particular point, the derivative is known. The slopes are right here. So we know which way we kind of are going. We do what we do not know if that turning, that if it turns left, turn right, turn fast, or turn slow, we don't know that. But the derivative is known, and therefore we just make a little step in that direction. Okay, so that orange step towards that is known, but it is an approximation of the unknown purple point. Okay, so that's the price that we pay, and the difference is the price we pay for approximation. So it can never be continuous. It can never be exact, but at least we know how to control that error. So we'll look into that a little bit. But basically, that's the basic. If you ignore the error, that's how we proceed one point at a time, and then repeat, right? So once you do that, you are in a new location, and now recompute the same thing at the new location and do the same thing, which means that the over here the other unknown curve might look like this. So you have jumped, unfortunately, to another curve. You started on some curve, but because the approximation did not stay on the curve, you went on the tangent, and then which means that you inevitably, if you try to continue on, you will be following a different curve, a different solution curve. These are the unknown solutions. Okay, so that's certainly is the price to pay, but sometimes if it is about motion or physical space and the change is continued, then the reality is this, and what's on the right is an approximation. If the change is incremental, it's the opposite, right? So the continuous is the approximation of the discrete or the incremental. Okay, so but in this case, let's suppose that the motion, the dynamics is continuous. Such as motion through space, continuous action, let's say forces of spring, strain, gravity, all acting on our object, and in which case the motion is continuous, but and we have to approximate because it's just too complicated. Okay, so this one is a big deal because the approximation. What's the name of this approximation? What's so special about this approximation? What kind of approximation is this?
Linear.
A linear approximation. That's right. The linear approximation, also known as, except you see, it's a one linear approximation, capital one, right? And then, but the difference is we're going to keep doing it again and again and again, as many times as you want. Linear approximation, linear approximation, linear approximation. Okay, so then naturally, it only works if our function over here is differentiable. So this is also called linearization. We're going to look into that quite a bit. A linearization what does it mean? It means replacing the curve with a straight line best we can. So it's actually not necessarily, sometimes better called the best linear approximation is what the tangent line is. And so linearization is replacing your non-linear function with the best linear approximation. Okay, so in that sense, okay. I just made up a word. Differentiable is linearizable. See what I'm saying here? So if, like absolute value function, it cannot be linearized at that point. You zoom in and it's still, that corner is not going anywhere. But if the function is differentiable, then that's another way to understand it. It can be replaced with this tangent line legitimately. Okay, so like I said, we will do more of that, but right now we kind of do it almost mindlessly, just linearize, move on one step, and then linearize again and move on. So linearization itself, there is no linearization. It's not happening. Linearization is what was behind it, but really we don't have to do it because the derivative does not need to be computed. It's already known. F is where the derivative is. So if we know t and y, we know the f, and therefore we know y prime. So the derivative will be always known without differentiation. So derivative is known. No derivative known without differentiation. That's the nature of differential equation. We know the derivative, and then we need to find a function. That's the challenge. And in this case, we turn it in our favor, so we can know the derivative without any differentiation. Okay. So anyway, so let's go back to concentric circles. I'm afraid they're just not. My picture's a little bit off. I don't like the picture because you ignore the match. I don't know if it makes sense. They ignore the colors. Because it appears that there is this red circle and it goes to the bottom. Okay, it is a circle after all, the whole circle, but the bottom half of the red half circle and bottom top and bottom red circles, half circles, they have nothing to do with each other. It's not a curve. As far as the ODE is concerned, they are not linked with each other. Okay, so there is a cut through my domain, and they separate top from the bottom, and therefore these two exist separately. And at least there's existence in the top and the bottom, and so in that sense, everything is fine. But it's also an illustration of what of the different domains. As you can see, for each circle, the domain may be short or may be long, and so we cannot, pick one and live with that, unfortunately. So that's a challenge. We did that example differential equation is y prime is equal to negative t over y. Okay, right hand side is negative t over y. Naturally, once again, let me do what I just indicated here. Dy dt is negative t over y, which is converted to delta y over delta t equal to negative t over y. And furthermore, delta y is equal to negative t over y times delta t. Okay, and then if you want to make one more step, it is 1n plus 1. Y plus 1 is equal to 1n minus t over y delta t. So the so pure algebra except for what this is the step is when you reverse the limit. Okay, so that's where the derivative comes from. It comes from a difference quotient. So this is the derivative. This is the difference quotient. The only way to get the derivative technically by definition is to take the limit of the difference quotient, and we just went backwards. And so since it's reversible. And then we will make it entirely into a sequence with a recursive sequence. So 1 plus 1 is equal to y minus t over y delta t. So if t and y are known and yn is known where we are, then we can find the next term anytime we want. So that's exactly what I have here. Okay. And then okay, so that's it. So we can just carry it out just the way we did it early on the first week of classes. Remember when we started not with a differential equation but with a model. And that model was discrete to begin with, so we didn't need to think about the derivative. And then when we're done with modeling or other simulation, then we took the limit and produced the differential equation. And now we just make a kind of step back before doing the numerical business. So this is the numerical business. Okay, so let's carry out a few steps of this just by hand, even though the computer obviously will do the job for you better, but you have to do it by hand just to get a feel of it. Okay, so let's choose delta t equal to 1 is what I'm doing here. Okay, the initial condition is t naught is equal to 0, y naught is equal to 1. Okay. And the subscripts are the indices of the sequences. So there will be sequence of t's and sequence of y's. T naturally progress one at a time. That's what delta t is. And then it is known, but delta y and y's will be to be found according to that formula over here. So if we know yn, we'll find y plus 1 according to this formula. Okay, so delta t1, so it's quite a bit simple. So okay, so let's see. So let me make it slightly. Okay, so I see the formula. I have a I have to correct myself here. This to make the picture complete, you have to add the indices here. Okay, so yn tn. Okay, so then nth terms of the sequence are known, and then from that we know the n plus first term of the sequence. That's what this says. Okay, so let's carry out the computation. So y prime, we will, that's what f is. It is that f is negative t over y. So every time we will compute it again and again. So in this case, because my initial conditions are t is equal to 0, so the whole thing is equal to 0. So y prime is equal to 0. So the graph unknown, we don't know what the graph is, but it has a horizontal tangent. So on the tangent we go horizontally. So our first step will be horizontal. Okay, so as I said, that this term will disappear. If it disappears, then a y t progresses by 1, but y does not progress. Okay, so so delta y is 0. Okay, as it indicates. So there is no change in the horizontal direction, and so that's the shift in my new location is t1 becomes 0 plus 1 is 1. And y1 is 1 plus 0 is equal to 1 once again. So literally move horizontally one step like this at the bottom. Okay, so we were at 0, 1 on the ty plane, and now we move the 1 unit to the right. And then you can guess, as we have done it with the computer, we do it one more time. But from the new location, my new location is 1, 1, so I have to recompute my right hand side, my derivative from this. Plug it in 1, 1 into my equation. So we have a new initial condition, 1 and 1. We plug them into my right hand side, which is once again with a negative t over y. Negative t over y is what is being recomputed several times. And so t is equal to 1, y is equal to 1, so it's negative 1. Okay, so my derivative actually, so this time once again unknown curve, but it's pointing down at 45 degrees. Okay, so once again on a tangent we go down at 45 degrees diagonally, and so then y1 is negative 1, but you can compute delta 1 very easily. It's negative 1, and then we end up with the t1 progresses by 1 every time, so it becomes 2, and y2 progresses by negative 1, so it becomes 0. Okay, so here we go, and so we have moved then over here. So that's the picture still applies on the right. So this is stage 1, this is stage 2. And look where we ended up. We ended up at 0. So here y is equal to 0. You can see why this is a problem.
The denominator.
Y denominator. So that's it. We break down, and my program holds. Okay, so because we cannot further divide by 0, which is felt like bad news, but on the other hand, we actually know what the answer is. They're supposed to stop. It just does, they did it in just 2 steps, and it doesn't look like a circle at all, but at least it stops, and it stops exactly where we wanted to stop. We were lucky. So that's just a 2-step solution. And okay, so it's not the end of it. We could here we stop. Let's pick another point. 1 point above, 1 unit above the original. So t naught is equal to 0, but this time we're starting 1 point higher right here. Okay, so t naught still is equal to 0, so y prime is still equal to 0. So our unknown curve, even though it curves down, probably its tangent is horizontal. So the first step is still horizontal. So delta y is equal to 0, and we're progressing. T naught progresses by 1, and we are moving on to 2. We're staying at 2. So in other words, the first step is exactly the same as last step. So this is what we produced on the first try, like this. On the second try, this is where we are, and then we'll see what happens. Now my new location is this. 1, 2, and this is what to be plugged in into once again my t negative t over 1. Okay, so to be plugged in into this expression one more time, and then you can see what the value is. Negative 1/2, right? So my derivative of the function that is unknown is equal to negative 1/2. Okay, and so which means that it will go down at slower, not at 45 degrees, that's the last one, but slower. So half a pace like this. Okay, so negative 1/2, we're moving on, so, 3/2. The new value of y, y2 is 3/2, so 1 horizontally 3/2, and then from 2 to 3/2 down, and that's my new location, and then this is my new location, that's my new initial value problem. We plug in, once again, this is a negative t over y, one more time, once again, these values are plugged into this expression, and then that gives me the new value of delta y, which is negative 4/3, and you see the problem? So y2 is equal to 3/2. Delta y is negative 4/3. Where do we end up if we carry out the step? If you, well, you remember algebra, how you do fractions anymore?
You would cross the,
You not cross technically, you jump, right? So we're not crossing anything because it's not a curve, but it is bad news because remember there is actually y equal to 0. The x-axis is actually kind of a wall chasm, if you will, and so the fact that we have crossed it is actually not good news, because once we do, what's supposed to happen next, if you can guess? If we cross below the line, what's gonna happen next? Which way we're gonna go?
Backward.
Back, right, because it becomes negative, we have to go back, and then what's in that, that's not good news, obviously. So indeed, once we get there, we either have to carry out or not carry out it at all, and then as you can see, indeed, then my next location is actually going up by 1/6. Okay, so that's the sequence right at the bottom is 0, 2, 1, 2, 2, 3/2 still okay, but then we jump below to negative 4/3, which is below the x-axis, and then we at least a little bit jump up in the opposite direction, which is not something, it does not look like a curve, not like a circle at all, the last step, and so that suggests to us that our method is really, that's a limitation, right? So we have to watch out for a place where things can go wrong, and that's usually where there is division by 0 in this particular case. So this is what this is, and we have reached that point, negative 4/3, and then if we were to go up, if we were to continue on, then what? No, we didn't. Hold on, we didn't. 4/3, 3/2. We did not cross. I'm sorry. I may have pushed too hard, but the 3/2 minus 4/3 is still above. So it is the next one will be bad. So 1/6. Let's test this. 1/6. Where are we the next time? It is 4, and hold on. It is negative. No. That's a typo. This is a typo, right? We end up over here. This is 1/6, right? That's a typo, that's exactly a typo. Well, confused me. So for 3/2, the delta y is negative 4/3. We move down, but it's still positive. We end up with 1/6. So we're still above the x-axis. The next one will break it down, because let's compute it. Delta y is equal to negative t over y again, and which is negative t being 4. Hold on, what's t? T, is it 4 or is it 0, 1, 0, 1, 2, 3? So it is still 3 over 1/6. Okay, so it's negative 2. Oh, hold on a second. Y is 1/6. No, it's not. It's a what's the answer? Fractions?
negative 18.
18. So that's right. So look at the jump. It goes down really hard, and it definitely crosses the x. Will cross the x-axis. So the end result will be over here. Will be negative 17 and 5/6. Right, so that's the next location of ours. So we will be way down, because why? Because the tangent is horizontal, vertical almost, and therefore we'll be going down very fast. Okay, so that's what happens not only when we touch where we did the division by zero, even if we can get close to the place where there's a division by zero, the things break down. Okay, that's what we're seeing here, and that's the unfortunate reality of approximation. You have to, so there are some generic places where everything works out fine. And then there are places as we just saw right here, like that, and then it goes, all the way down somewhere, in which it becomes negative, and the next one you will have to jump up, okay, because of a reversal of the direction. The tangents above the x-axis are negative and below is positive, so you have to jump up. Okay, so something that you don't really want to do by hand, so we're gonna do it with the computer in a minute. But let's summarize. It's called Euler solution. Okay, so it is a historical name. So as you can see, we started with the same thing, and we called it simply the difference equation, right? That's simply the difference equation. So why is it Euler equation? Why is it called Euler equation solution? Because it is a historically Newton-Leibniz. They developed calculus, okay, and differential equations, which Newton was very fond of, and he solved a bunch of them. But then things, as you progress to things that are more complicated, then you run into things, differential equation that you cannot solve even then. So it was like the 1700s, and they already had differential equations that were unable to solve. So Euler invented this way of as a new thing, in a way, I suppose, of how to approximate solutions. So. Right now, where we are in a very different place historically. So we're not starting with those calculus 1 and 2 as we learned what Newton-Leibniz did. So everything is done by hand. Okay, and then when it works out, you have to approximate. We are in the opposite place. We probably better start with the approximation. It's not an approximation, but rather start with the discrete model difference equation. And then you take the limit, and maybe you do some work by hand to try to solve the system if you like. So it's a bit of a reversal of the order, but nonetheless it is, as you can see, the same story. It is circular. You start with difference equation to ordinary differential equation. Then if you go to both back to Euler's method, it's the same as the difference equation that you started with. Okay, so we're talking about the same thing. Okay, so let's do the same thing as last problem, but with a spreadsheet. Okay, so first of all, it is solvable. Okay, so we can verify that our differential equation at the top does produce a bunch of circles. Okay, so implicit circles, and so but let's do the brute force, and let's face it, that's what Euler's method is. Brute force. You need a computer, especially that's for more force. And then, so that's equation. This is my formula once again. So it's just a division, as you can see, and then I progress one step at a time. What we did by hand, now we just make the computer do it for us, as we did on the first week of classes. So that's what it looks like. Okay, so the blue one starts. This time I started at 5. Okay, no, it's 3, and then I made a delta t very small, not 1. We started very crude, and it might give you the impression that that was the problem. One on tx is 1 at a time. It is inevitable, right? It's going down, so eventually it will reach the x-axis, and the trouble starts. That's what the blue curve is. So it dips below, it accelerates first of all, and then it dips below the x-axis, at which point it wants to come back, and then it comes back again below and then above, and then if it hits, that's the last point that you see here, if it gets real close to y equal to 0, then what happens if you divide by a number that is close to 0, you have a very large number, and so that jump doesn't even fit into the picture. Okay, so that's kind of to be expected, and then no surprise then the second experiment with the red curve, it produces exactly the same effect. Eventually it runs away. So Euler's method, as you can see, is universal and seems like it is a very powerful thing, but that's what can happen. It might run away because it is ultimately an approximation. Okay, so it looks very much like a circle, as we would expect. Not exactly like a circle, but kind of circular. But then when it reaches this kind of a troublesome area, it misbehaves and maybe very badly. I remember we said that we had that example with the when we looked at the jar, population of bacteria in the jar, we also had the jumping up and down. So it behaves erratically. If you know what the correct answer is, here I decided, well, I know what the correct answer is, so let me stop before we get into trouble, and that you actually do get a pretty picture. So Euler method produces these nice pictures, as long as you stay away from the x-axis, then everything looks very good, and they do look like from below, from above, they kind of almost touch each other and turn and make this half of a circle. Okay. Okay, so hyperbolas, just the same example, just let me show you once again, we know the differential equation. It is solved in terms of logarithms, it produces hyperbolas. If we try to do it by Euler's method, that's what happens. Once again, everything is fine, but as it crosses the or gets close to the in this case zero x-axis, there might be a jump. And because of the, not only the troublesomeness actually is, no, troublesomeness here is here. This is the cosm is the y-axis. So if you start too close to it, which is what this point is, at the top is too close to the y-axis, the change is so fast that it might be actually bring you to across the x-axis. And instead of going down, as you're supposed to gradually go down like this, but actually jumps, and you end up on a different curve, on a different solution. And that solution is actually not only a little bit different from the where you're supposed to be, but really, really different. So because instead of going down, it's going up, and that's what you see here. That does not look like if you look at the blue curve here made of these dots, it does not look like a hyperbola at all. Okay, so the hyperbola, this part looks like a hyperbola, right? But this one, this one does not. So like I said, it jumps from one curve to one solution curve to another, and that may be okay if these curves are just close to each other, or it might be very, very dramatic as what you see. Okay, so once again, if you know where the trouble lies, and that's where the trouble lies, right here, then you carefully can plot these nice pictures. But remember that is you're hiding under the carpet, swipe under the carpet, certain things that should trouble you. Okay, so, and if you encounter something that you've never seen before, then you actually are supposed to seek these problems rather than try to avoid them. Okay, so there are more examples you can try on. So that's all about Euler's method, really. The only thing remains, which we unfortunately probably have to skip over, is how close is the Euler's method to the reality. Okay, so it actually can be figured out. Okay, so all right. So the third possibility or not possibility, but rather they are all part of the plan. If you do not have an explicit direct analytic solution, then you do theoretical analysis, numerical analysis, and now third is qualitative analysis. And none of these require solving the solution, but it requires really good knowledge of calculus nonetheless. So qualitative analysis is similar to a qualitative analysis in calculus 1. Well, what do you remember from calculus 1? Looking at the derivative, it tells you something about the function. Without finding the function, right, which would be integration, nonetheless, you can say a few things about the function from nothing but the derivative. What is it?
Whether it's growing or
Whether
it's growing.
Increasing, decreasing, okay, the sign of the derivative, and that almost it. You can throw in also what? So derivative positive, function goes up, derivative negative, function goes down, and if you want to add, if you want to be a little pedantic, then you might also consider derivative equal to 0, so that's max min. As you can see, look at the logic goes actually backwards. If the function is increasing, then derivative is positive. If you have maximum minimum, then derivative is equal to 0. No, not the other way around, but it works out fine for our qualitative analysis. Okay, so then, like I said, unlike calculus 1, where you're supposed to find the derivative, right? So find that prime. and then draw conclusions. But we don't have to do it anymore, right? So ODEs, it is known. Even though one point at a time, but nonetheless, the derivative is known. And so we at every point where we know the slope, right? What the slope field tells us exactly that. So every time we know that our unknown solution will be going up or down or equal to 0. So we did a few times that already, and so let's just do more of that. Qualitative once again. So it's a qualitative meaning up and or down, but not how much. Okay, so quantitative would be actually numbers attached to it, and that's numerical method. The numerical analysis applies, even though there is an error there, but it's at least it is quantitative. You can actually tell where we are rather than just which way we're going, roughly speaking. Okay, so once again, that picture we've seen already, autonomous, which we probably stick to initially, autonomous differential equation without t present. That's what autonomous is. Right here, and then so as we can see, the slopes are the same as you move horizontally. So the change of t does not change the slope. That's what this picture is supposed to be. And then you just follow the arrows. And except this time we're not gonna follow the arrows. We'll just we're gonna just say what it is. Okay, rather than trying to build. So not this anymore, but rather just to say, we'll say here this. Just words, that's positive is up or increasing. And here you say decreasing. That's what we're going to be saying. It's like 90% of what we care about. Increasing and decreasing. So we describe it with words what's happening depending on the region, right? So as you can see, depending on where your curve is going, it will be different. So below that line, it will be going to be decreasing, and above will be increasing. And there is the special, that's really, even though it seems to be an exceptional and the one single curve, the straight line, actually it is an important one, and it is ultimately is what we'll be concentrating on more than on the rest, because these are easy. It is the singular points in what this horizontal line are the interesting ones. Okay, so what can we draw? What conclusion can we draw about it? About the solution set if we were not to solve it, and then that's what logistic equation that we have noticed is it's not entirely obvious if you look at the graphs. Logistic solutions, once again, slow growth in a jar, slow growth and fast growth. They're slowing down when we reach the capacity of the jar, and then with asymptotes on both sides, fine. But turns out that all these are all the curves are identical. They just shifted horizontal. So if you're not sure, you would do it with that's what I did here with the computer. The data on the left, you plot the Euler's method or numerical method on the right, and then as you can see, you look at two consecutive or adjacent solutions, and the 2 points are separated by exactly the same distance. Okay, so literally, if I take the blue curve made of those dots and shift by this violet shift, then I will produce the other one, the one made of dark red dots. So all the solutions differ by horizontal shift. So there is basically only one solution, and that qualifies as qualitative analysis too. So just saying that because the equation is actually, it's not nothing about logistic equation specifically. The fact that it is the equation is autonomous because there is no dependence on t. Then the curves will be, you can see it on pictures over there. The curves will be identical as far as the location differs, but not the curve shape of the curve. Okay, so that's what we end up with. Once again, same story with exponential. That's the difference. This is the regular population growth, and once again, you see just a shift of these seemingly very different exponential functions, but actually they do differ by nothing but by horizontal shift. They are identical. Okay, so let's look at it. So antiderivatives. So shifts. We've seen shift in calculus 1. Right, so that's what on the left. You have what amounts to a differential equation. The simplest differential equation is on the left. Okay, so that's the differential equation that comes from calculus 1. y prime is equal to f of t. You solve it by integration, and then if you have one solution, then you get the rest of them by doing plus c. Okay, so vertical shift will produce all the rest of the solutions. If you have your differential equation, which is new, somewhat, then and we found one solution, then how do we find the rest of them? It is the same story, only the shift is horizontal. Okay. So once again, if y is a solution, then so is z. So because there is no y on the left, that's why the shifts are vertical, and there is no t over here on the right, then the shifts are all horizontal. Okay, just like these examples show, indeed, the shifting one single solution gives you the rest of them. That's why we only need one solution. So that's good news. Just like in calculus 1, we say no one, no all, except you have to know which way to shift, how to produce the rest of them. And as you can see, it's a little bit more subtle where C is on the inside. That's how we execute horizontal shift. We change the input variable, not the output variable. So over here it is Z that is affected by C, and here it is T that is affected by C, and that's why the shift is horizontal. So to summarize is once again, suppose the right hand side of the an ordinary differential equation is independent of t. Okay, so let me put the word here. It is well, it's called autonomous. Okay, so that's the terminology we're going to use. And then if y is equal to y of t is a solution to the ODE, then so is y equal y plus t plus s for any real s. Okay, so s is a parameter, and for each s, I don't know why I put s here instead of c, but I think it is probably better idea just to put c here to make the point, to make a link to calculus 1. Okay. Shift, just a different kind of shift. Yeah.
I thought autonomous was not dependent on C or T as a variable.
Yes. Yeah, that's the case. Look at it. There is no t here.
Okay, but the integral that is dependent on T.
The integral, yeah. So the one on the left. Right. Look at so that's the crucial part is this one. The right hand side of the equation depends on t, saying y prime is equal to sine t. Or it's not, y prime is equal to, say, y squared.
Oh, I didn't see the two
Okay.
columns up there.
So when you have an ODE, it's always gonna shift horizontally instead of vertically.
Right, always. So naturally, remember, we've had examples when the function depends on both t and y. So it's neither integral on the left or nor autonomous on the right, which makes it more complicated. But these are most typical because the direction of where you're going depends on where you are, not what time it is. That's what it is. So it's a flow that hypothetical in a pipe that never changes. Okay, so at every location, all the time, if you are standing at the same location, the flow at that location will be exactly the same at every moment of time forever. Okay, so that's when there is no t in the right hand side. When there is, it means that the pressure may be changing in that pipe, and that complicates things a lot. But this one is a particularly important case on the right, and it is really complicated too. It's not like it's a very simple. We still face all the problems of differential equations that we can think of. But nonetheless, there is such a nice thing that there is basically one solution. Just one solution to worry about. If we find one, we find all. Okay, so back to what we just started with, qualitative analysis for calculus 1. Monotonicity is determined by the sign of the derivative. Okay, so derivative positive going up, derivative negative going down. Change of the sign of the derivative indicates maximum minimum. But when there is no change of the sign of the derivative, then there is no maximum, no minimum. That's the rightmost picture over there. Okay, so once again, that's the summary. Remind you how it is. It is a good way to describe it is the sign analysis. So we're sign of the derivative. So it is sign analysis. So once again, usually we found in calculus one, we had a function find its derivative and then analyze the sign of the derivative depending on the value of the input. It gives you different signs and therefore different behaviors of the function, and then you might plot the function. We're in a very similar place, except there is no need to differentiate because the derivative is to be found easily. But nonetheless, if you're going to remember how it happens in calculus one, that's how. So you have a function, then there's a differentiation, and then you look at solve what amounts to an inequality where the depending on the value of x, the derivative it might be positive or negative. So so the idea is the same, except the function is now not of x, it's of y. Okay, so so let's keep in mind that the wiggles are possible. So even though we know which way we're going, the knowledge of the derivative does not allow us to eliminate the bottom three possibilities. What does? The nicer picture at the top row, that's how we would visualize. The function is decreasing, then increasing in the top left. Okay, and that's how you would visualize it, roughly speaking. But why do you do it this way and not the one that below it? What's with the wiggles? What's responsible for the wiggles? What?
Like its derivative,
Can I say it again?
like it'd be changing in slope. Like slope would be
What?
that
If the
value.
derivative is trigonometric.
What?
If the derivative is trigonometric.
Well, yeah, okay, the derivative is trigonometric, what trigonometric functions do especially.
The sine and cosine.
Right, but they change the sign themselves, right? So there is a particular function that is responsible for that. What function is responsible for the change of the derivative?
The second derivative.
The second derivative. So the wiggles come from the change of the derivative. And then that how do we know there's a change of the derivative? We'll look at the second derivative. So if the second derivative remains the same, remember it is responsible for concavity. And then so the top picture has the same concavity roughly like this, while the wiggles are the change of concavity. So we will have to look at the second derivative too. So like I said, everything for calculus will come up. Okay, so that's my differential equation. Sign that we're looking for. Let's just look at the some examples to begin with. And so this one is a non. So I jumped straight to the non-autonomous equation. Okay. Okay, so we need the sign of f for let's be clear. So we need the sign of f for monotonicity of y. Okay, we don't care about f this time. So that's the letters that I have been using may be slightly misleading because f is not what we differentiate. So let me change that actually to make that point clearer. Y's are the function, the derivative of which we'll look at. Y is that is a known function. So like this, and this is let's call it y2. So what is the f is the right hand side of my differential equation, and it doesn't need to be computed. It's already known. Okay. So, but here is so that's a good picture right here. So we're not looking at y f anymore. We're looking at y. Y is our function, the derivative of which is known and is used to say something specific about our function. Okay, so so then sign of f is the derivative of y, and therefore we're looking at the sign of f in order to determine which way y goes. Okay, so we want to know y is the solution that is unknown, and we want to know which way it goes by looking at the derivative of y. If y is not known, then its derivative is unknown, which means that we cannot really compute it, nor can we use it directly. But the way we do it is just to look at one point at a time on the plane and look at the sign of f. Okay, so then the difficulty then is that in non-autonomous case, especially, there are two variables t and y, and then f depends on it is defined now on the whole rectangle, possibly qy plane, and then each point has plus or minus attached to it. Okay, plus, minus, minus, plus. Okay, so and then we know that if our curve y passes through over here, it will go going up, and here it will be going down. Okay, so that's what we can do. That's what the qualitative analysis is going to be about. So, okay, so that's one example. The function of two variables. This time it's not autonomous, as you can see, t is present. Therefore, what? As you can see, we would be looking at these are the slopes. Okay, so we could try to build that curve here, but really it's not. We're not gonna, so that would be Euler's method, but we just look at the signs, and you can see these negative and positive signs very clearly. So the pink one is positive, the rest are negative, so which means what? Can you envision what the curves, we're not gonna be speaking of one curve anymore, but rather of all curves at once. So what does the curve look like if the white is negative and the red is positive? What?
Like an upside down sombrero.
Yeah, well, yes, but no, I mean the curves, the solutions, the solutions supposed to, the numbers are the slopes of those solutions. What would they look like? What? Well, you can't really use that language here. Because, like I said, because we don't know what the curve looks exactly, we only can speak in very general terms. So negative. Here's one, that's a solution, right? So plot a few. That's because over here, all these numbers are negative, which means that the solution will be going down, and this one too. And here, all of these are down rapidly, right? But here they will be going up. Okay. So can you imagine one solution that is complete solution? This is a complete solution, that is a complete solution. But what if I start, say, over here? How will it go? No. How it seems to be going towards the red area. But before it crosses the area from negative to positive, what's going to happen? What lies between negative and positive? Zero. So what the tangent will be zero. So the curve will be horizontal, right? So it will get in like this. Okay, and then it grows, and then how do we get out? Once again, it has to get out in a kind of a maybe, no, not like this. I don't think it's going to get out. Hold on a second. So it starts growing, and then it will slow down, and then I'm not sure what's going to happen exactly. But like I said, it only can get out in a manner that is across from positive to negative in a horizontal manner. Okay, so it probably will have to go like maybe like this and get out here somewhere, maybe like this. Oh, I have a picture that follows. Like this. Okay, so slopes are inside of this circle, there's a pluses, outside of minuses. On the circle, there's zeros. And then if you plot them, that's what you're gonna get. So very rough picture. That's the way we're doing best job we can, but try not to make it, pretend that we know what it looks like. So if we know it's going down, that's we can just draw a line like this. And that's because that's we can know. We also know that inside of the circle, they will be going up at some angle. I put 45 degrees because I don't know. And then, but we also know that it's going to cross the circle itself horizontally. Okay, so these are three types of pieces can be conceivably connected to each other, as I just tried to do, to create full curves. Okay, so this is one of them that might look like this. Once again, do it usually by hand. It goes down. It slows down as we're reaching closer, getting closer and closer to the circle, slows down, becomes zero, crosses it horizontally, then goes up. Once again, as it gets closer and closer to the edge of the circle, it once again becomes horizontal, gets out, and then starts to decrease. Okay. So like I said, so the differential equation given by the data on the left or the function here on the right will behave like this. So some of them will be totally straight or maybe straight, we don't know if it's straight or just decreasing functions, but the wiggle will be in the middle. That's the only way to pass this circle in the middle. Into the circle, well, actually, the point is actually holds here. Look at it, no formula. Naturally, this data came from some formula, but the all analysis as well as the picture itself do not invoke the formula, right? So you have a bunch of table of numbers, and then you can color them as we did before. We can plot the function of the variables. Once again, if you haven't seen calculus 3, maybe that is something new to you, but nonetheless, it is a function of the variables is visualized or by its graph, and the graph is a surface where inputs are on the horizontal plane and the outputs are the elevations. Okay, so the meaning of that graph is there is no meaning to it. It's literally just the value of the derivative as depending on where and when we are. T and y, the plane, and then the vertical is y prime ultimately. And so we know which way we're going. And so all the graphs lie in this ty plane, and that's how they behave, going from left to right in a decreasing mostly manner, but in the middle they make that wiggle. Because the this is the zero plane, z equal to 0 is this plane, and the tip of that surface protrudes above it, and that's where the derivatives are positive, and the rest of them are negative. Okay, so that's what we're supposed to indicate here. So this plane is z equals 0. And so everything below it, so maybe like this, yeah, everything below it. So over here, it's y prime is negative here, and y prime is positive there. Okay, so that is what we say is what do you call it? A portrait. A portrait, so unlike a photograph, if you will, I would have maybe to explain the word. Unlike a photograph, it's drawing. Okay, so from indirect information about the solutions, which we still do not know, there isn't even a formula. Nonetheless, we can draw a very rough picture of the solution set. Okay, so once again, there is no other information, but okay, so maybe this one so there is no formula, and at the bottom I actually do the opposite, and then I provide the formula. So maybe just erase it so that there would be no temptation to actually try to explain what it looks like from the formula. This is the qualitative analysis, and it ends with a portrait. And so, well, the portrait technically would have to contain all the curves like this. So that's supposed to maybe like this. Okay, so all the curves have to be drawn roughly, and frankly by hand. And the hope that you can do better if you actually do the Euler's method, and then it produces a similar picture. And so they kind of interact with each other and help each other. Okay, so once again, okay, to summarize what we just we've done now. Suppose y is a solution of the ordinary differential equation, non-autonomous. Okay, within an open set of the ty plane. That's the ty plane. This is the t here and the y there. Okay, and then function is defined on that plane. So which means that the pattern of zeros and negative and positive values is totally arbitrary within that plane. And then, but we can analyze. So analysis of signs will be more complicated, because what we did in calculus 1, it was a function of one variable. This is a function of two variables. So the complexity of this distribution of pluses and minuses could be way more complicated than this, and it will be shortly. But nonetheless, what we can say is that whenever that function is positive, we have increasing behavior of all the solutions, and then when it's negative, all the solutions that are inside of that region will be going down, decreasing. Like this. Okay, so if that's how the data is on the left, and the sketch on the right. Okay, so functions are increasing, so you can then visualize them in this manner, even though, like I suggested, if you do it like this, it's just as good, because we don't know. We don't know nothing about how fast they're growing. We don't know about anything about the concavity. So this is just as good. Okay. So that's an extra piece of information here. Is also important that if the derivative, if the derivative is 0 at the boundary of the region, the solutions will cross it horizontally. Okay, so if over here, that picture does not match it, by the way, so because then the only way for these to get out would be in a horizontal manner like this. Okay, if this was true, and this is the region with the zero in its boundary, then the only way to get in or get out would be in a horizontal manner. Which means that incidentally. Yeah, so how do you get out and then out and out, you can actually kind of bounce off of it. Okay. Okay, so autonomous, now if it is autonomous, then let's simplify the picture. So then remember, the autonomous means that F does not depend on T. Okay, so that's as we saw it, no T. Which means that it is still a function of two variables, let's be clear. So looks like a function of one variable, but it is a function of two variables. Because, well, why so? Because our solutions are still, graphs of these solutions are still on the TY plane. So it's just beneficial for us to not to oversimplify it and still think of this function as a function of two variables, just happens to not depend on T explicitly. So like f of ty is equal to y squared. Think like this. So y is not there. So if I change y, there will be no change of the output. But it's still, we think of it as if it's defined on the whole plane. Okay, so okay, so this is the interesting conclusion then, among other things, is that we can have a constant solution. So when the derivative is equal to, when f is equal to 0 for one particular value of y, then that value is the constant solution, as we see a couple of times. A stationary solution, a singular solution, any of those solutions will be appropriate. Naturally, it is. The proof is not much of a proof because it's almost obvious. So y is equal to a. So y prime is equal to 0, which is also equal. So that's the whole proof right here. Y prime is equal to 0 because it's constant, and then which is the same as the value of f of a, f of y. F of y is equal to 0 when y is equal to a, and so there's a match on the left and on the right, and so at every point, no matter, this is true for all t, why so? Because there's no t. Okay, the whole thing that doesn't seem to be dependent on t in the first place, which means that it will be true for all t's. Indeed, that's how we identify a very important solution to a constant solution. So there's all kind of dynamics, but there's one solution that actually is not changing. So the examples that we have seen of stationary solution were a city with no population, right? A city with no population because it never takes off. In a jar, if the jar is full to begin with, okay, so it will stay horizontal. What else? Constant. What other models did we have? Population, temperature. If you bring your coffee, which already has room temperature, then it's not going to change. So it's stationary. Radioactive decay, all of those things will also have a stationary solution. And the complexity emerges when you have a bunch of them. So that's when things become so a bunch of stationary solutions. Okay, so that's what we're looking for. Domain, by the way, also to worry about, that's once again calculus, pre-calculus. The domain of the function will be except the function of two variables, and where it might be undefined. And if it's undefined, then there is no solution as well. And so that would be cutting our portrait into pieces. So yeah, so imagine that here somewhere, that's when we're doing portrait, and it's undefined here somewhere. So then it will split our solution set into two unrelated pieces. So let's carry out one computation all the way through, or one analysis all the way through. So in this case, this is a differential equation right here. Okay, y prime is equal to negative tan y. Okay, so and once again, we're not going to try to solve it, even though it's probably solvable. And then we're going to analyze tangent or negative tangent in this case. Okay, so depending on the value of y, the tangent positive or negative tangent, then it has the opposite one. So this is the graph of the tangent on the y, let's say z plane right here, y z plane maybe. Okay, so naturally the curve of the graph does not matter to us. What matters is this is pretty much it. This is the answer. Or not the answer, but at least the first step towards the answer is, the only thing that matters is the sign of the function, which means that positive tangent, positive, well, we haven't solved the problem yet, so we know that what we're after, so it's not the answer really, but it's more of a question. So the question is, when z, here z is positive, z is negative, and where the question is, for what what are the y's? For what values of y, the z will be positive, and for what it will be negative. So you see from this picture what kind of pattern emerges here. You tell what happens to the y's. Well, above the x-axis, above the y-axis rather, everything's positive. Below it's negative. So these are good. These will be producing positive values over here. These are positive values, positive, and this is positive, but the rest will be negative. Okay, so and then the behavior of the function will be function will be different in different locations, and then we have a very rough sketch of the portrait of the solution set of our differential equation. Okay, so I'll stop here. So next time.